Hello, my name is Luke and welcome to this PyTorch tutorial series. In this video, we're going to look at latent diffusion transformers. If you're new to the channel, all the code you see here is available in my GitHub repo, link in the description, and this video is a part of a larger PyTorch tutorial series, and you can find the playlist on my channel. So in the previous video, we looked at latent diffusion, this idea of instead of training our diffusion model on the image itself, what we do first is encode our dataset with, say, an autoencoder or a variational autoencoder and get a compressed representation of our image and then train a diffusion model on that. The idea being that we can have a more computationally efficient diffusion model if we're training on a smaller latent representation. So if you haven't seen it already, I recommend you go and see that video first. In this video, we're going to look at the idea of using a transformer as first explored in this paper here, instead of a U-Net that is typically used for diffusion. The transformers now are very popular in a range of applications, and image generation through diffusion is a new one. A lot of the new image diffusion models are transformer based, especially the video generation models. They all use transformer architecture because of their flexibility. But in this video, we're going to see how we can train our own diffusion model from scratch to perform latent diffusion. So we covered the basics of latent diffusion in the previous video. The first step being we need to extract or encode all of our images into our latent representations. And in the previous video, we showed how we're going to use Hugging Face's models and its pre-trained autoencoder to do that. So we're going to skip most of that in this part here. So what is the difference between our transformer and our U-Net for diffusion? Well, the transformer we're going to be using is basically just a encoder-only image transformer. We've covered image transformers before in our image classification with transformers video, so if you're unfamiliar, you can go check out that video. But our basic model architecture is exactly the same as that encoder-only image transformer model. We know from our image transformer that the first step is to patchify our input image in order to embed our image as a sequence. Once we've done that, we pass it through our encoder model and then we get our output. The main difference between our diffusion transformer and our classification transformer is that instead of just projecting a classification embedding to get our classification outputs for our diffusion transformer, we're going to project all of the embeddings to the output dimension to get output patches, and then we'll rearrange those output patches into an actual image. So we have that extract patches function that we saw before that will patchify our input. But we now have a reconstruct function that will take that sequence of patches and reconstruct it into our image. So much like our U-Net, we also need to tell our diffusion model what stage of the diffusion process we're up to. And we're going to do the same thing. We're going to use a conditional norm layer in order to inject the information of what time step we're up to into our model. And you can go back to the very first diffusion video for more information on that. We have our time step positional embedding and so on. And I'm just going to skip to our transformer block to see that change here. You can see we've replaced that traditional layer norm with a conditional layer norm, and we've just replaced that single layer norm in our transformer block so that we can project or introduce that time step information into our transformer. Apart from that, the architecture is very similar, as I said, to that vision transformer for classification that we saw before. You can see in our overall diffusion transformer that as well as having the patch in, we also have a patch out to create the output patches. And the last thing we do is reconstruct the image from those patches. Everything else in this code is exactly the same as the latent diffusion we saw using the U-Net in the previous video. So we have the same code size schedule, we have the same diffusion process and everything. Once we create our diffusion model, the training process again is exactly the same. You can see here we create our diffusion transformer, and you can see we're using a patch size of 2. Now this is quite a bit smaller than the patch size we're using for image classification. And we're using such a small patch size because in the original paper, they actually find that the smaller patch size is better. So they actually train a number of different sized transformer diffusion models. They have a small, big, large, and extra large. And for the same sized model, they train it with a number of different patch sizes. So they train an 8x8, 4x4, and a 2x2. You can see for the same model with pretty much the same parameters, just changing that patch size greatly improves the image quality. We have our FID score here, where lower is better in terms of image quality. And you can see just by changing the patch size, we get a large improvement in performance. In fact, if we skip to the end, to this table here, you can see that a small transformer with a 2x2 patch, this only has 33 million parameters, gets a FID score of 68.4, and that FID score is pretty much exactly the same as the big transformer with a 4x4 patch with 130 parameters. So the FID score is pretty much the same. In fact, the FID score is better than even the extra large transformer with an 8x8 patch. So that patch size is definitely an important parameter. We want it to be as small as possible. However, as we know, with a smaller patch size, that means we can have a larger sequence length, and that means more compute. It'll be more computationally expensive to train a model with a small patch size because that means a longer sequence, our attention maps are going to be bigger, so on and so forth. So basically, I'm going to have a 2x2 patch and have the largest model I can around that 2x2 patch that I can fit on my GPU here. The hidden size of the embeddings, 768, and 10 of those blocks, which is actually smaller than any of the other models in that paper. But again, I want to have a patch size of 2. Let's go ahead and run this. And as per usual, I've already trained my diffusion model here. I'm just going to load the parameters again. You can see I trained this model for a little bit longer than the previous one. I trained it for over 1 million time steps. And this again took a couple of days. So if you want to replicate this, you need to wait for a couple of days. So we can look at the results. Okay, so there we go. Got a bit better results this time. Our model is a bit larger and we did train for longer, so we'd hope for better results. Now, if you did want higher quality results and with a better implementation, this implementation is just for educational purposes. The original code used for that paper is available, so it's from Facebook Research, and it is all written in PyTorch because PyTorch is maintained by Meta. So you can actually go download this code, train your own model using one of the presets from that paper, or you can define your own. I'd actually recommend going to this FastDIT version. So that was the original code used in the original paper, but they've made some updates to make it faster and more efficient. This FastDIT allows you to actually train a model faster and actually allows you to train a larger model even on some low-end hardware. So for my 2080 Ti here, I've actually been able to train the small model with a 2x2 patch size. All right, for the rest of the video, I wanted to look at some of the things we can do with a trained diffusion model. There has been some interest, especially after the previous video, at techniques such as image-to-image and image inpainting that are commonly performed with a trained diffusion model. Image-to-image refers to taking one image and transforming it to another. Image inpainting refers to replacing or painting over certain positions in an image. And both of these things can be done with a diffusion model that was not trained to explicitly do that. In this next section, we're going to look at some of these techniques. Now, these techniques can be applied to any image diffusion model, not specifically a latent transformer-based diffusion model, but that's what we have here, so that's what we're going to use. So the simplest method of image to image is to take a source or target image and noise it up a bit through our forward process and use this as the start of the diffusion generation process. So normally in our diffusion process, we start when we're generating with an image of just random noise. We put that through our diffusion model and we get an estimate of what the final image is of a person maybe. Of course, from the random noise, this is going to be a really bad blurry estimate. And so that what we do is we take this estimate, we put it back through our forward process and get a noisy version of this image. So it'll be mostly noise with, maybe slight face there. Put that through the diffusion process again, get a new estimate of what the original image was. And this is going to be slightly better. So this is at our first time step, 0 time step. And we do this over and over and over again until we hopefully get something that looks like a good image. What we can do instead is, instead of starting at time step 0 with just pure noise, we take an image and we noise it up a bit. Again, as defined by that forward process. So it'll be noisy and some detail or information is going to be lost through this process, but then we use that as the initial starting point for our diffusion process, right? That's going to estimate the final image again, and then so on and so forth, for the rest of the diffusion process. So if this was at time step 100 and we had 500 time steps, we would then do this for the remaining 400. The closer you go to the start of the forward process to just pure noise, the more different the final image is going to be to your target. And then conversely, if you go very close to the end of the forward process or close to the start of the forward process and aren't adding that much noise, then the generated image won't be that much different from your source or target image. So we can do this with our model. All we need to do is get an example image. I've just got this example image of Obama. It should be there in the GitHub repo as well. And we're going to use this as our starting point. So we have a look at that. Here's Obama, very large. And we're going to noise this up to some point and then diffuse to the rest of the process. So you can see in the actual diffusion process code, I've got this additional parameter here called start step. Again, that just defines where in the loop we're starting from. Normally, this is 0 by default. So I'm going to take this image and I'm going to noise it up. First, we're going to extract the latents, in fact, because we're doing latent diffusion. And then we're going to noise it up by some index. So we're going to start at time step 300 and then go to 500. So we're going to take this, noise it up. Here's our noisy input, put that into our cold diffusion process, and also tell it where we're starting from. So we should only have to do 200 steps here. And we can look at our result. There we go. We have the original image here and all of the other generated images. So we're generating 8 images at a time. And you can see we're starting pretty close to the end. And so the images are pretty similar with some fine detail changes. So we can make this even closer to the start, let's say 50. And we would now expect our images to be quite a bit different. There we go. So some similarities in the actual position of the head and head shape, but they are quite a bit different to the original image now. That's quite a simple technique to do image to image, but we really can't define too much about what we want to do. It's kind of just up to the model to do whatever happens. So image in painting is a way to specify a bit more about how we want the image to change, particularly what spatial area of the image. So with image in painting, what we're doing is we're only allowing our diffusion model to generate a certain part of the image by masking off the generated part and putting in our target or source image. So to explain what I mean, let's go back and I'll draw it out. So normally when we want to generate an image from scratch, again, we have our image. That's just all noise at the start for the very first time step, t equals 0. We have our big diffusion model. And then again, that tries to estimate what the original image was very badly at the start. And then normally what we do, as I said, is just put this, noise it back up into our forward process. Time step equals t equals 1 now. Our image, mostly noise again, faint image there, and then same as before, put that to our diffusion model, and again estimate the last or the original image. What we're going to do now with image in painting is modify this image, this noised up image that goes into the diffusion model. Instead of putting the image as is in, what we do is we have our source image, we again noise it up to the same time step, so time step of 1, which is going to be mostly noise again, the faint outline of our source image. And what we do is we're going to combine these two together, but replace certain parts of this image that was sort of generated and noised up with parts of our noisy target image. So let's say I only want to replace the face in my source image. What I want to do is remove that spatial region from my noisy source image, replace it with the area of my noisy generated image. So what I do is I need to define a mask, which can be just a binary mask for simplicity, that kind of outlines the region. So if this colored in region here represents 1s and the non-colored in region represents 0s, what I can do is I can multiply this by my noisy generated image, and that will 0 everything that's not that center region. And if I multiply my noisy target image or source image by the inverse of this, it will 0 the region where the face is and keep, say, the background. Then all I need to do is add the two together, and then I'll get a resultant noisy image that has the face from the generated noisy image and the background from the source noisy image. So I multiply this target noisy image with the inverse of this, so inverse multiply by this, get this, and then we multiply that directly with our mask, and then we add the two together. That gives us our new noisy image, and then that goes into our diffusion. So a bit complicated, and then we predict the final or estimate the final image again. And we do this for every single time step of our diffusion process. We need to noise our target image so that it contains the same level of noise as the model would expect. So we can't just shoehorn in the source image here with no noise. We need to noise it up to the same level as the generated image before we do our masking and addition, and then we put that through our diffusion model. And like I said, we do this every single time step. So we need to define a new diffusion process that I've done here. And you can see we take in the sample, which is going to be the initial random noise, but also the target and the mask of the region we want to replace. So with my target image, we noise up the target image to the same level as the input random sample or the generated sample. And then we interpolate basically that random sample with our noisy target as defined by that 2D mask. And then this is what goes into our diffusion model. We do all our estimates to get the new random sample, and then that goes in to again be interpolated or mixed with our noisy target that has now been noised up to the next level of noise, so a bit less noise. And we do that over and over again until we get our final generated image. We're basically forcing the noisy generated latent as it goes through the diffusion process to be what we want it to be. And then the diffusion model has to sort of work out what the rest of the image should be in order to match that. Because we're sort of giving it information about the image, and the model has to sort of generate something that matches that as well. And so hopefully we'd get a nice blended image. So to see an example of that, we can just define a very crude square mask. So we've got ones in the middle, zeros on the outside. And this is 32 by 32 because that's the size of our latent. We only need to generate one channel of this, and then it will broadcast across all the channels and all the images in the batch. So again, we're going to generate 8 images, and we're going to provide our source image, which is again Obama, but as well, we have this mask. Okay, let's have a look at our results. So there we go. So the diffusion model has only replaced the section in the middle, which roughly correlates to the face of our target or source image, and everything else has been kept exactly the same. Only that middle section where that square was defined, the square of ones, has actually changed. And you can see our diffusion model has actually nicely blended that new generated information with the original source information. We can also invert the mask as well. So instead of replacing the face and keeping everything else, we can keep the face and replace everything else. So let's have a look at that. So we're just inverting it here. Okay, let's have a look at the results. And there we go. And we've got our generated images that have kept that center square region, and our model has tried to generate something that matches that for the rest of the image. You can see, however, that using that crude square mask has caused our images to be a bit funny. You can see the center region of the head seems to be very square, as the model is, maybe generating something that wasn't quite square, or wasn't quite a square face, and then has had to, make it or force it to be square. And so we can help our model a little bit by defining a nicer mask that we can use instead that better defines the facial region. So instead of just crudely defining a mask, we can use a nicer smooth mask that we've actually defined and constructed from the original source image. So there's a lot of generative tools out there these days, like Google has on its new Pixel phone, that allow you sort of to draw over your image and then generate something there, or replace what was there with something new. And what you're doing by drawing on your original image is defining this mask in a sort of smooth, fluid way with your finger. That's all you're doing. You're just defining this mask, and then Google's using one of their pre-trained models to do this exact same image in painting. So we can define our own mask, again, based on the source image. Well, I've just gone Photoshop and actually drawn around the face and defined this actual region that defines the face. And I've also just created another mask that defines the silhouette of Obama as well. We can use these instead to actually do our in-painting. I actually created these masks from the full-sized image, and we're actually downsampling it here. So you can see that the edges are actually a bit blurry. That's okay, because those will be values between 0 and 1. This is actually good and can help our model because it's going to basically smoothly interpolate the noisy generated image and the noisy target or source image together, so it's not quite a hard boundary. So let's use these masks instead. So the first one I've got here is just the face mask tensor. So basically we'll be replacing just that face region again. And again, we've replaced the face while keeping the background exactly the same. You can see it is a bit smoother, the actual interpolation between the two images, and the faces kind of fit a bit nicer. But just like before, we can invert this mask and keep the face and replace everything else. And there we go. That's a bit nicer of a face swap there. You can see in this one in particular, that's pretty good. The generated head nicely fits the face. Even some of these other ones are good. You can see in this one here, it was trying to generate a face that was sort of tilted to the side, which didn't really match it. And that does happen even with high quality models as well, but you can get some nice face swaps. So let's have a look at the background. Let's use this one now. And if I were to just put it like this, what we're going to do is we're going to keep the background and basically generate a person that has the exact same silhouette as Obama in this image. There we go. The background is exactly the same, but we have new people and they all have the exact same silhouette of his head. But maybe we don't want to generate new people. Maybe we want to keep the photo of ourselves, but change the background. So if I invert this mask, we'll keep the face and the head, but we'll just change the background. There we go. Same face, but we have a different background. And you can see it has sort of smoothly tried to interpolate part of the background still. So you might want to move the mask a bit tighter around the head. You can see we've got a different background for the same face. Now I've actually done this for myself with my own image, so you can see the original image here and all of the different images. So changing the background and then keeping the background but changing the actual person, changing the face here, and then we have these ones here where we've kept my face and got it to generate a new body or person around that. So you can do it with your own image as well. What you will need to do for an image of yourself is align it correctly. All of the images, if you're using the Celeb Face HQ dataset, as I'm using here, you'll need to make sure the image is aligned in the same way. All of the images in the dataset have the eyes in the exact same location and they're sized correctly. I just ripped some code off somewhere ages ago and I can't find exactly where it's from, but there are GitHub repos online like this one that will do the correct alignment. It is the alignment for the FFHQ dataset, so it's the same alignment process. They've just, I think, taken it from the actual NVIDIA FFHQ dataset. There is code buried in here that actually does it. You can use this repo. If this is too hard, maybe I can try to put something together to align it yourself, but you can align it and then go through the same process once you've trained your model to do the face swapping and things like that. Okay, that's all I wanted to cover in this video. We've covered a few different things, but as you can see, we're starting to look at some more advanced techniques. As I mentioned in the previous video, we're going to go back, revisit some of these algorithms and look at them in a bit more detail and implement some more advanced techniques, again, all from scratch. You can do all of this face swapping and in-painting and things with some larger pre-trained models from Hugging Face and the like. But hopefully you got something out of this by doing it from scratch and seeing exactly how it's done. Of course, if you want a more general model, you'll need to train on a more general and larger data set, which means you'll need a larger model as well. Here, everything we're doing is just with faces because that's the data set we have and the model we've trained. But in any case, if this was interesting, remember to subscribe and I'll see you in the next one. Thanks.